Kind of. Well, anyway. So this talk is going to be, there'll be no, it'll be kind of, what's the word, speculative. I want to discuss some questions which come out of Manjul's heuristics. Okay, so let me describe in the way. So Manjul gave some very beautiful heuristics based on his computations for low degree of how many fields of given discriminant there should be. So basically what I'm going to do, I'll take those heuristics, I'm going to apply them in places where they have no business being applied. And they won't work, but they're very wonderful heuristics because when they don't work, they fail for interesting reasons. Okay, which in a way is a nice, better than them working all the time. So they're very, so we're just going to see what happens in some different settings. So as I said, so Manjul wrote down these heuristics for Sn, but I think there's something we should take seriously in general as a guide to what happens. So let's suppose let's say we have some number field k, and yeah. Who said that? Oh, okay. So, okay. No. How big do you want this? Okay. S is okay. Is that good? Okay. All right. Okay. So S is some set of places, and the kind of question we want to ask is how many. So okay. So G is some finite group, and we want to ask how many. The sort of question we're interested in is how many field extensions of K, how many field extensions of K with Galois group G. So let's say this is a finite set of places. How many field extensions are there unramified away from S? So how many G extensions? So when I say this, what I mean is, so some field extension, so just shout if this writing gets too small. So some field L containing to K together with, so with Galois group isomorphic to G. So we'll when we get to it, I'll say whether we want to specify an isomorphism or not. But the basic sort of question is, how many G extensions are there unramified away from S? Okay. So what Manjul's heuristics give us is some sort of expectation of how many on average we might expect. So let me formulate a version. Well, so as I've stated it here, just an isomorphism of groups. Okay? Yes, yeah, so sorry, implicit in this I mean, yeah, okay, so Galois, yeah. Yeah. Okay, so let's write down what the heuristic is. So the heuristic is roughly that the expected number should be a product of local factors. So we'll say in a second what we might mean by expected number, but it should be a product of local factors. So what is expected number? So what is the number we're counting? We're going to count the number of to make this look uniform, the way I'll say it is like this. So so GK will be the Galois group of an algebraic closure of of k bar over k. And so what the thing we're going to count is we're going to count conjugacy classes of surjection. So surjections from this absolute Galois group to G, let's call them rho. And then we count them by 1 over automorphism, as Manchel does. So in other words, 1 over the centralizer of rho. So that's the number of elements of G that, so in this case, it'll just be the size of the center of G. So because I'm assuming so equals the size of the center of G because I'm assuming rho to be surjective. Okay, and now, oh, sorry, yeah, so let's, all right. So plus some local condition. So let's say, well, I haven't written what it's equal to. So let's say unramified, unramified outside S. And S, that's now, it should contain all the infinite places. How do you do it? Okay, unramified test. So it's a product over places in S of exactly the same thing, but taken over homomorphisms of the local Galois group. Okay, so sum over maps from the local Galois group, so into G, no longer surjective, so let's call it rho V, so up to conjugacy. Under G, yeah, up to G conjugacy of 1 over the centralizer of rho V, and that's the centralizer in G. So centralizer in G. Okay, so just an yeah. Oh, okay. So this is okay. So what is expected number? I mean, we sort of pick some k and s, and we sort of measure it, and when we expect okay, what does expected number mean? So as I said, I'm going to try to use this as a kind of rough guiding principle and see what happens when so expected number, we might interpret it in several ways. Okay, so one thing we could do is we could fix the field K, and we could vary S, and we could ask that this holds. So let's call this equality star. So we ask this holds on average. So ask if star holds. Ask if star holds on average with respect to S. Okay, that is, so you sum over, say, sets S ordered in some way. Okay, the exact. So I mean on average. So you for example, something like this. So you take just so you might take the sum over all sets S such that the product of the finite elements is less than some n, and then you divide the left-hand side and the right-hand side. And you might ask that this go to 1. Okay? The norm of the place V. So I'm saying we look over some family of sets S. I'm not making a specific conjecture. I'm just saying this is the sort of thing one might mean by expected.
But I don't understand this.
Yeah.
Remember, it's unramified outside this finite set S.
What do you do about the surjectivity in this equality?
Sorry, where?
You want your row to be surjective.
Yeah, on the left here. Yeah.
Why do you expect equality?
No, no, okay, okay. So this was not a correct. This is the expected size. So expected, to make sense of this, you need to. I'm saying such a thing. Well, I don't know what to put here. When you average over some of the various things you could average over, the two things asymptotically are equal. That's the kind of. Okay, so for example here, you could fix the field, you fix the group, and then you average over all sets of places with norm. So this corresponds to discriminant counting in the usual sense. Okay, another thing we could do is we could not, rather than we could, so fix the set S. So for example, let's fix it just to consist of all infinite places and vary the field K. Okay, so the kind of question we might ask here is the sort of, which this will give some prediction for, is on average, how many unramified, let's say, S5 extensions does a cubic field have as you vary the cubic field? Okay, so that's the sort of question to which this would predict an answer. For okay, and the third thing you can do, which is completely nuts, is you could fix K and S, and you could vary the group G. Okay, so here's an example of a question of this sort. Are there infinitely many Sn extensions of Q which are unramified outside the fixed set? Well, let's say unramified outside 2 and 3. And now n, so for where n, so n can vary. All right, so my box of white chalk go. All right, so the idea is, here is perhaps, so this is a little bit insane, but this makes some prediction of some sort of expected number. If you add up that expected number for n, you can ask if it's infinite or finite, and whether or not that has, that sort of matches, I mean, to what extent what this prediction gives you makes any sense or has to do with reality or whatever. Okay, so this thing is sort of I think sort of the furthest of all from the context in which Manjul made these, because he was talking about degree D extensions for fixed D, and I'm saying, well, let's see what happens when the degree goes to infinity. But so that's an example. And so, all right, so this is the type of settings I want to talk about, but now I'm going to be more precise, and we're going to discuss sort of one example of each of these where we'll see what this says and where something goes wrong in one way or another. Are there any questions up to here? Yeah. Yeah. G is a fixed group, yeah. It's a sum of, well, 1 over the size of the center. I only wrote it like this to sort of match the way the... Yes. So z of rho. Sorry. Well, this should be this. Yeah, this means the size. But yeah. So this quantity is a constant of size 1 over the center of G because rho is surjective. I just wrote it this way so it looks more like the right-hand side. Okay. Yeah. Any other questions? Yeah. Center of G. Centralizer in G. All right, so there are 3 things I want to, well, I guess, so what I'll discuss is the first thing I want to discuss, and this is, I mean, whatever I say is sort of joint with Jordan Ellenberg. So the first thing I want to say is when the Schur multiplier of the group G is non-trivial, it's not just has size bigger than 1, the expected number of fields can increase. From increase relative to what you would what this predicts. Okay, so there's some kind of extra factor which is not a product of local things. So I'm going to do just rather than, so in fact, I don't know exactly the most general form of this, but I'm going to discuss 2 cases. The first case I want to discuss of this is what happens with the Cohen-Lenstra heuristics for cubic fields and for the two-part of the class group of cubic fields. Okay, so this is something Mungial mentioned. So Mungial showed that the average size of 2 torsion was as expected. But something funny happens, for example, if you look at the second moment of that. Okay, so I'll discuss where that fits into as an example of this. So and then the second example I'll talk about is A5 extensions of Q. Okay, so also, the relevant things here, the groups here, the group in this case will be Z mod 2 times Z mod 2, and the group in this case will be A5. And the relevant point in both cases, the Schur multiplier is non-trivial, and that will increase somehow the expected number of fields. Okay, so that's the, or at least we think it will increase the expected number of fields. So in this case, there's a lot of numerical evidence due to Mala. This case is. Okay, and then the second thing I want to talk about are questions of this sort. So are there infinitely many either SN extensions with fixed ramification set and ramification set, and then the same question for PGL2 FP, and so in both, so here n can vary. So I'm just asking if there are, and here p can vary. So the kind of question is, does the Galois group unramified 2 and 3 have infinitely many quotients of the type like PGL2 FP for some p? Okay. Oh yeah. So I'll discuss this over Q. And so yes, of Q. So I don't have answers to either, but I just want to say how this heuristic motivates you to look at things which seem to be interesting. Yeah. Okay, any questions before I start? Okay, so let's do the first thing. So let's talk about this how this Schur multiplier makes a difference. And so first of all, I want to explain maybe what happens. So I think the way we came to this by thinking about what happens over a function field. Okay, so first let's talk about what happens over C. Okay, so over C, so in other words, rather than considering Galois extensions of number fields, I'll consider extensions of function fields over the complex numbers. Okay, so in other words, so we're sort of seeing what happens as we go on through this analogy between Q and something like, well, let's say a function field of a curve over C, function field of a Riemann surface, or let's say a number field, function field of a Riemann surface over C. Now, so over here we were considering extensions of number fields, so L over K with Galois group G. Okay, so here what the corresponding thing is we have, say, some X, which is a compact Riemann surface, and we have a covering, another Riemann surface covering it with Galois group G. Okay, so okay, so in other words, if we pick some base point, so choosing a base point, you have a map. So the analog from the Galois group to G, you have a map from the fundamental group of X at this base point to this. Okay, and I'm going to assume it's, yeah, sorry, this is a covering. So this is a topological covering. Yeah. Oh, okay. All right. So, sorry. Yeah. So, I should allow ramification in this picture, but just for the simplicity of discussion, let's start with the case where it's a covering. And when I say let's start, I also mean let's finish with the case it's a covering. Okay. No, so that's just, and the reason for that is just because when we add in ramification, there'll be some similar picture, but it's a little more complicated, and I don't want to spend time on. I just want to see where this H2 comes in. The point is that these coverings have that. So to any such covering, I can associate. So to this data, okay, to this data, I can associate an invariant in H2 G with coefficients in Z. Okay, so I'll explain how to do this explicitly. But the point is, so in other words, if this Schur multiplier is non-trivial, there are different topological types of covering. Okay, so if two coverings have different invariants, you can't deform one into the other. Okay, so the way that manifests itself over a function field is that when you try to count G coverings, there's some moduli space. That moduli space has multiple connected components, and that makes it have more points than you would otherwise expect. Okay, so I'm going to define this so that there's sort of lots of ways you can see this invariant, but I'll define it in some sort of very concrete way so that we can see the analog over a number field. So you know the all right. So now let's yeah. So I'm just going to define this so in the case when the genus is bigger than 2, the other case is not very interesting. So genus X is bigger than 2. So what that means is the fundamental group is it has a presentation, a standard presentation is generated by 2G elements, A1 up to AG, B1 up to BG, subject to this relation, the product of their commutators in order should be the identity. All right, so now this Schur multiplier, what it is, it's essentially the kernel of the universal central covering. So let be a universal covering. So this term is not precise when G is not perfect, but what I really mean is so that is a central extension G tilde of the group G by the Schur multiplier. If G is perfect, this is literally universal among such central extensions, and if not, you can choose one that has some sort of weaker property. And the way we're going to define this invariant is we're going to see what happens as we try to lift this map from pi 1 to this covering. Okay? And the reason I'm sort of going through this is I want to replicate it in the number field case in a second. Okay? So we lift each. So we have some homomorphism here. So let row of AI, you lift each one of the images, be a lift of row of AI and row of BI. And then you take the product of their commutators, and that is then independent of choices. Okay, so then the product of all the commutators is row AI. So this is some element of G twiddle, but it maps to the identity in G. Okay? So this has to live in H2 GC, and it's independent of choices. Okay, so that's all I want to say about the complex case for a moment, because that's going to motivate. I'll try to write down some analogous construction over a number field in a second. Are there any questions? Okay. So this is. So I'm sorry. I mean, I have to say, like, a lot of this I kind of learned from Jordan telling me. So what should I write? Okay. Yeah. Okay. Sorry. So yeah. I mean, one thing. This is not. Yeah. So certainly not due to us, but I don't know the. Yeah. Oh, IE. I'm sorry. I shouldn't have agreed to this being videotaped. All right. So what, roughly speaking, do I want to try to do now? So I want to. How do we expect this to manifest itself over a number field? So the statement you have to take with a grain of salt, but so roughly. And the word roughly is because you have to take into account, how many roots of unity you have is very important. But roughly, so if you had enough roots of unity, we would expect something like the following to happen. When this is not trivial, so when this has size h, so over a function field, what happens is you can sort of split the covers into this many different types. Okay? So what would happen over a number field is we expect h times as many G extensions. And again, another reason this is imprecise is there's a version with ramification which looks slightly different. We as expected. So as expected means relative to what you would get if you took. And but there's a more precise thing, we can divide G extensions into H different classes. Okay, so you can sort of account for the fact there are H times many by actually dividing them up into H different classes, which are kind of an analog of these topological types, such that each occurring with the expected frequency. All right, so let me now make this, I'll make this precise in a couple of cases. As I said, there are two reasons this is rough. You have to account for roots of unity, and you have to account for ramification. Okay, and that, I mean, so to get the formulation right in general is quite delicate, but that's roughly the picture. There are more fields than you expect, so that's some number field. All right, so let's do the first case. Where did I say? Okay, so what happens, class groups of cubic fields. So all right, so K is going to be a cubic extension, a cubic field, and I'll call n of K right. So yeah, okay, so let's call C of K the class group of K. And just so, I mean, this doesn't matter so much, but we're going to look only at totally real fields, just so I don't have to keep dividing. No, I'm not, but I'm going to make some statements on average over cubic field, and so the question of whether or not you included Galois ones wouldn't make a difference. Okay? So the Galois ones behave differently, but okay, so you should think of, yeah, so it'll make no difference, but mainly we're dealing with non-Galois in these. If you put the word non-Galois, nothing would change. Okay, so the number, so homomorphisms from, say, the class group to Z mod 2, these parameterize unramified, including at infinity, unramified quadratic, quadratic extensions of K, so by class field theory. Now, let's see if we still have the heuristic up here. Nope. All right, so according to the heuristic I said, now the number of such things, so we're looking, they're everywhere unramified. So the expected number, and after I write this, I'll say exactly what this translates to. The expected number is just a product over the infinite places. So there are 3 of them. Okay, and then of the 1 over. So we're counting. So expected number of homomorphisms from, well, okay, the unramified part of the Galois group to Z mod 2Z. Okay, so remember we had to multiply this by 1 over the size of the center, so 1/2. This should be the product over infinite places of the same thing. So
are these the surjective ones?
yes, thank you, surjective, and this should also be surjective. Thank you. Sorry, absolutely. Yeah. So on the right-hand side, we have a product over infinite places of, well, sum over homomorphisms from the local Galois. So this is just of the Galois group of R to Z mod 2, 1 over the Z of rho. But now, if we're looking, these are everywhere unramified, including at infinity. So in other words, we're looking only for totally real extensions. So this is trivial. So this factor is 1. It's a half at each of the 3 real places. Okay, so it's 1/8. So in other words, what this predicts, which is as the Cohen and Lenstra heuristics predict, is that the expected. Okay, so So what does it mean exactly, expected number? So the prediction is that, so now expected number means we average over cubic fields. So sum over cubic fields with discriminant less than x, so all right, always totally real cubic fields. The number of surjective homomorphisms from the class group to Z mod 2 divided by the number of fields. Okay, so the prediction then is that this should approach 1/4. Okay, and this despite the fact it doesn't numerically look true, has been proved by Munjal. Okay, so this is a theorem of Bhargava. Okay. All right, so that all looks good. Now, what happens if you look at the second moment? Okay, so suppose I put a Z mod 2 times Z mod 2 here. Okay, so what happens, yeah, if you make this a Z mod 2 times Z mod 2, well, what you get over here is 1 over, instead of half cubed, a quarter cubed, you get a 4, so you get 1 over 16. So that's this is a prediction that this, and this, as has been noticed for a while, and so is not, so this prediction seems to be wrong, and Mala has given a lot of evidence, so experimentally, and Mala has given a lot of evidence that the right answer seems to be 1/8. Okay, so this, so right, all this is experimental, but the data here is due to Gunther Mala. Okay, so now from.
But wasn't the other one also wrong experimentally?
Yes, yes.
So what?
I'm very selective in my use of data. Right, so no, but so here there's good, so there's theoretical reason also. So I'll explain how this fits in. From our point of view, what is the difference between Z mod 2 and Z mod 2 times Z mod 2? This one has a non-trivial Schur multiplier. Schur multiplier has order 2, and so this that is the, so this is twice of the correct answer. I mean, it should be twice of the predicted answer. And now I want to make a more precise version of this corrected. Okay, question? All right, so the corrected prediction is that the expected number in the sense that I said before, so expected size of the number of surjections from the class group to Z mod 2 squared is 1/8, and as I said, so from our point of view, what this 1/8 is, it's the 1/16th, which is corrected by the size of this Schur multiplier. And now I want to refine this. So even more precisely, we can divide. So we can in fact assign, so more precisely. So I want to do something which is analogous to dividing topological, the covers in the complex case into two topological types. So I want to, we can do something like that here. So we can assign to each homomorphism, so each surjection from row to the class, from the class group to Z mod 2 squared, an invariant, just like, so I'll explain an invariant, so I'll call it Z of row, which lies in this H2, which in this case is plus or minus 1. And So the idea is once you sort of fix this is the analog of this topological type, then the original heuristic should hold. And then so we would conjecture that that there's, so to speak, 1/16 of a row per sign. Once you fix 1/16 of a row per cubic field, once this is fixed. Okay, so along with the fact that this is off, there comes a natural way you can try to fix it by dividing them up into parts, and each part should behave as you might have naively hoped. Okay, so I'm going to explain how to assign this invariant, and this will be fun, really. Okay, are there any questions? Yeah, so, it is in the process of being tested. Yeah, so my student Simon, who's sitting over there is testing it. If it doesn't work out, now is not the time to bring it up. All right, so definition of Z of rho. But actually, maybe there's one thing I want to say about, so even if you don't believe this sort of function field analogy, you can see by pure thought that this heuristic can't hold for all groups at once because it's incompatible between a group and its central cover. So even if you know nothing about function fields, you can see the heuristic I said, if you compare what happens for a group and a central extension, you see something is not quite right. So one of them has to be off. So that doesn't tell you what the answer should be, but it tells you that something must be. Okay, so if you recall what happened over the complex numbers, I took a homomorphism for some pi1, and I kind of tried to see to what extent it would lift to a covering group. Okay, so the invariant I defined had something to do with how this lifts. Okay, so here's what we're going to do. So we're going to start with a homomorphism from the class group of what's the same from the Galois group of our cubic field to Z mod 2 squared. And now we're going to lift it to a covering group. So for example, we could take the dihedral group would do. So the dihedral group with 8 elements, it's a central covering of this with kernel, plus or minus 1. Okay, so I start with this, and now I'm going to lift it. So lift to rho from GK to D8. Now, this original row was unramified. Okay, so I started off with a map from GK to here, and now I'm going to try to lift it. Okay. Now, one can do this, and the reason you can do it, depending on how you think of it, because you have the question of whether or not you can lift it is something in H2 of the Galois group with coefficients plus or minus 1. So you can lift it as long as you can lift locally. Okay, so, or more concretely, if you're trying to physically lift this thing, basically it comes down to solving a bunch of quadratic equations. And if you can do it locally, you can do it globally. Okay, so this can be done because it can be done locally. And it can be done locally because it's everywhere unramified, so it's very easy to see you can do it locally. Now, the only thing is, though, this may not be, rho tilde may not be unramified. In fact, usually it'll be impossible to make it unramified. So I have to write down some invariant which measures somehow our inability to make it unramified. Okay. All right. So now, but how much ambiguity is there? If you lift this, you can twist it. So you can, by twisting rho tilde by a quadratic character, you can make it very nice. Okay, so can arrange that it's unramified at any finite set of places you want. Okay, you can fix it at any. So let's say unramified at primes above 2 and at infinity. Okay, so trivial at infinity. So every complex conjugation is trivial. Okay, so we, yes, and you multiply by the map, right? And so so because I can arrange that map to do anything I want at a finite set, I can fix anything I want at a finite set. And now out of this, now I want to extract from this a number. That number will be 1 if you were lucky enough to lift it in an unramified way, but otherwise it sort of measures how. So I'll just say it, and then I'll say why it's. So here's how you define. So we define the invariant of Row to be the parity of the number of places of ramified places for rho tilde. So the number of places where for rho tilde, and keep in mind, when I say rho tilde, I've made this preliminary thing, such that the number of places V, such that the norm of V is congruent to 3 mod 4. Okay? And the reason for this last thing is now suppose I twist it. If I twist rho tilde by a quadratic character, by some version of Stickelberger's theorem, this set changes only by an even size. And so the parity of it remains unchanged. Okay, so this is independent of rho tilde by some version by some sort of Stickelberger type theorem. Okay, so the prediction then is that this divides up the sort of these thing we're looking at into 2 sets, both of which look of the right size. Yeah, so it would be well, it should be determined by this. I don't think I've actually have we checked this, Jordan? I don't think you can get any other. If you take a larger central covering, this will be determined by. Yeah, and I think Q8 should also give the same answer here. Right. Yeah, the only reason I'm slightly different is whatever we actually wrote for a perfect group G. So we haven't sort of thought so carefully through this one, but it should work the same way. Okay, so this is now, because, where's Mike? Oh, how much time do I have? Well, wait, I did start it. Are these 50-minute talks? Or are these an hour or 50 minutes? All right, is everyone, are you, I'm not going to ask you. Okay, so there is now this story is, I think the more interesting part of the story is for something like A5, but for reasons of time, I want to sort of skip to part 2. Maybe the one thing I should say is the general story, you have to fix it for ramification, okay? So it's not quite as simple as what I've, if you look at fields with ramification, it's not exactly the Schur multiplier, but some quotient of it which depends on ramification, which is the relevant thing. But the story is general. In fact, I mean, one thing I've been teaching this class on the geometry of numbers, and something I noticed is even there's a very similar story. If you look at the mass formula for quadratic forms, okay, so there's a mass formula which says the mass of the genus of a quadratic form is a product over places of some local masses. But even in this formula, there's a 2 here, which comes from the Tamagawa number of the special orthogonal group. And again, this is a very similar phenomenon because what happens over a function field, if you write down the analog, the point is over a curve, there are 2 topological classes of orthogonal bundle. Okay, so so even the classic mass formula, there are this sort of some integer correction which comes from. One way to think of it is in a geometric analog, the corresponding space has multiple connected components. So that's kind of the general story we expect when there's a non-trivial Schur multiplier. Okay, are there any questions? I'd like to go on to this. Okay, so let's talk first about the PGL2 FP case. So So let's go back to our, so as I said, it's, so question 2. So we'll talk first about PGL2FP. So fix some set S. So this is of places of Q. Let's say, yeah, containing infinity. Yeah, fine. Yeah. I guess all I wanted to say here was, yeah, the number field is Q now. And so what we want to ask is, are there infinitely many PGL2FP extensions? So for some prime P, unramified at S. Okay. Yeah, for varying P. So P is, so yeah, so if, are there infinitely many extensions for some P? That would be a lot easier. Okay. Outside S. Now, let me just say before we go on, we have lots and lots of ways to construct such extensions, but not so easy to get them to be unramified at P. Okay? All right, so first let me say what Manjul's formula says about this, and then that sort of, well, okay, because I'm short of time, I'll give you the short version. So Manjul's formula says the expected number, and as I said, this is Manjul's formula applied outside where he's licensed it. So, okay. There was a box of white chalk somewhere here. Okay. Okay, so the expected number of, surjections from the Galois group of Q unramified S to PGL2 FP, so surjection. So if you go through counted up to conjugacy, if you go through what that heuristic says, it gives you that it should be something like a constant which depends on S divided by P, okay, or P minus 1 or something. Okay, so first thing is all right, so if you allow yourself all P's at once, you have this sum, okay, some constant over, so this is certainly infinite. All right, so if you, so very heuristically, this you might expect this to suggest that there really are infinitely many PGL2FP extensions of this type. Okay. Now, it even this reasoning, it's even true for S to empty set. Okay, and of course there aren't very many extensions which are unramified nowhere. So you can't take this. I'm not saying you take this literally, but the point I want to make is this: there is something interesting here. So okay, so I think this goes back to a conversation Jordan and I and my student George Sheffer had a couple of years ago, and so we started thinking about if you could produce many such extensions. Okay, so where does one get? So by the way, I don't know the answer to this, but I think it's probably it might well be true, and what's certainly true is there are very, very many such things. So where do we get where can we get such extensions from? And one way you can get them is you can get them from, well, you can get them from modular forms, but you have this, so, all right, suppose you have a modular form of level n, which is divisible only by primes in S. Oh, let's say Q and S, L and S. So this gives you a Galois representation. Now, if this modular form happens to be a weight 1 modular form, modulo P, okay, weight 1 form modulo P, this gives you, the weight 1 is, so weight 1 modular forms are magical because they give you, at least for P is not 2, you get out of this an unramified, a Galois representation to GL2FP, which is actually ramified only at S, not at P. Okay, so this is an absolute miracle. Now, there aren't very many weight 1 modular forms. Okay? So they might, when we were discussing this, a couple of years ago, as far as I know, the only, but maybe there are many weight 1 forms modulo p. The only examples that we knew of were due to, I think, Merel and Gabor Visad, and that's for p equals 2 or p equals 3. So I told my student, George, go and compute modulo forms, weight 1 modulo forms mod p, not really expecting an answer. Sorry, George. But anyway, so George came back about a year later, and he found something kind of amazing, which is that there are actually an enormous number of, so I'm just going to say this informal, I'll give you some examples. There are an enormous number of non-liftable, that is, they don't lift the characteristic 0, non-liftable mod p weight 1 form. So if you go look at a level which is moderately large, like in the hundreds, very rarely will you find a weight 1 form. But if you look mod p for OP, you'll usually find a colossal number of them. So for example, one of the bigger examples George found was at level 993. He finds an example with p equals, it has so many digits I can't even figure out what the right if it's a million or, okay, let's see. Okay, so 5 billion. And this is very generic behavior. So for all large levels, he found I'm not doing justice to this, but so it's probably, so I don't know, it's almost certainly the image to PGL2 is full. George? Where's George? Is that right? Yeah. So it's very rare for it to have small thing unless it lifts the characteristic 0. Okay, so these are extremely common. And so this is, I think it's a very interesting thing to look at further. The reason I mentioned this context is just it's something which we kind of start to think about only because we start to think of this heuristic, what this heuristic says. All right, so there's more data, but I don't have more time. Just a couple things. So by and large, Mungel's heuristics are roughly compatible with what we know about Galois representations coming from modulo forms. Okay, so there's more. You can say this about look at other groups and so on, but they're roughly compatible. But there are some very interesting cases like this one where somehow there are many modulo forms where we didn't really know they were. Okay, so all this and more is computed by George Scheffer, and this is okay. Maybe the other thing I should say, this has also a very interesting connection to analysis. So you can count the number of mod p weight 1 forms in a suitable sense by a special value of a Selberg zeta function. So it might be possible to prove such a thing as well, but I don't know. Okay, let me just say, now let's talk about Sn, which is, I think, the most interesting case of all. And again, as with everything in this talk, I don't actually know the answer. But so the question is, so fix a set S, are there infinitely many Sn extensions? So can you find infinitely many Sn fields ramified only at 2 and 3? Ramified outside S. And here n is allowed to vary. So do there exist? Oh, allow n can vary. Okay? Yeah, so what I wanted to get at with this really is what we have, if we fix a set of places S, we have some understanding of what kind of finite groups that the Galois group on ramified there maps to. For example, we certainly have a whole bunch of representations coming from modular forms. But something like this, not only I think we have no idea, we have no sort of way to think about whether or not such a thing should be true. Any guesses? Again? Well, at least it was a different error this time. Okay, unramified outside S. All right. All right, does anyone want to guess the answer, which I don't know anyway, so Sure, yes. Anyone else? Anyway, so here's what I think the answer is. I actually think this will be true for some S's, but not for others. Okay? So what does the heuristic say about this? So Mungel's heuristic, again, let me skip to the expected number of Sn extensions, blah, 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 well, it says that it's equal to something, well, it's bounded by some constant to the n divided by n factorial. The constant depends on the set S. Now, let me just say roughly, the n factorial comes from the Archimedean place. The point is there's not too much contribution of the other places, and although, you can just compute it, but the idea is that for there to be a very big contribution from a place P, the P Silov subgroup of the group you're looking at has to be large. So the P Silov subgroup of Sn is not so large. All right, so the point is that the sum of this, so this is the opposite situation, the sum of this over all n is finite. Okay, so this might lead you to believe that there are only finitely many, and that is what I thought until David Roberts produced this amazing example of a field of degree 15,875, which is unramified only at 2 and 5. Okay, and to believe that that's something impressive, you can go and compute what this expected number is, and you find it's completely negligible. Okay, and so after that, so Roberts and I started working together, and we have this kind of conjectural construction, at least for some special sets S of things we think will give infinite families of these. Okay, it doesn't work for all sets S. So I don't, for as far as I know, and I probably believe, so probably there are only finitely many when S consists of a single prime, for instance. Okay, but I don't know, but I no longer believe that there are always, I think for example, when S is 2, 3, and 5, I think there probably are infinitely many such fields. Okay, so I don't know, but clearly there's something very interesting here to understand. Okay, thanks.